Hello and welcome to Lecture 42 for my class, From Data to Decisions. I'm Chris Mack, your instructor, and this is our first lecture on multiple regression. We're going to have a number of lectures related to topics that are unique to multiple regression, and this is the first one. What is multiple regression? Well, it's simply regression against more than one predictor variable. And there are a couple of ways to do that, a couple of ways in which this happens. Excuse me. The first case is I have one input variable, but I'm using it in different forms in my model. So if I only have one output with one input variable, we call that bivariate data. But we can have a model that has multiple terms that make use of that single input variable. A simple example is a polynomial. Here I show a little bit more complicated example where there's only one x, but I have x in the model, I have x squared in the model, and I have the log of x in the model. And from the perspective of the regression itself, each one of these terms, x, x squared, and log x, can be thought of as independent predictor variables, independent terms. And sometimes we don't know exactly what the right form will be, and we're going to try out different things. Sometimes we have a theory that guides us and says we need to include these terms in the model. Sometimes we use polynomial models as a kind of a generic, I'm not sure what the form should be, but let me try out different numbers of polynomial terms. Sometimes we justify that because almost any function over a small enough range of x can be well approximated by just a few terms of a polynomial because it's the Taylor expansion, the Taylor series expansion of some function, a more complicated function, an exponential, a sine, whatever. Often we can look at the terms in this case and learn something about maybe the unknown function. Thinking of the polynomial model as a Taylor series, right? Do odd and even terms, powers alternate in sign, for example. The relationship between linear and the squared and the third power coefficients that is somewhat simple. We can learn this. I do that kind of thing a lot. Start with a polynomial model and then maybe turn it into something more complicated based on those fits. In any case, this is one example of where we would use multiple regression even though we have bivariate data. But sometimes we have multivariate. So this would be the second case. I have more than one input variable, and I want to include them. So in my example, I have two variables, x1 and x2. So I could have a linear term in x1 and a linear term in x2. But I can also have more complicated terms that, in fact, include both of them. So here I have a third term that is x1 times the log of x2. Who knows why that might be important in the model, but there it is. One thing that we can think about, an important thing to think about, is the interpretation of the coefficients, betas, for the case of multiple regression. We sometimes call them marginal responses. If I were to hold all other variables constant, and I asked how do I get a change in y hat, a unit change in jth predictor variable xj, well then beta j is that change. It's the change in our predicted y, or the mean value of y, per unit change in xj. All of other variables being held constant. So it's good to keep that interpretation in mind as we go through various multiple regression exercises. The mathematics of multiple regression turns out to be identical to the mathematics of regression with only one input, only one predictor variable. We approach a maximum likelihood estimator in the same way. Find the likelihood function, take the derivative with respect to each parameter. We get a set of p equations for p predictor variables, and actually p unknown parameters. And we simultaneously solve them all. We get an exact solution. How do we do that? We do that with the matrix method that we've already talked about. Every new variable just adds a new column to the matrix, the design matrix, and that gives us another set of equations that need to be solved. But the way in which we solve it is the same, and the mathematics looks the same. If we use ordinary least squares regression, which we can do with multiple regression just as well, I get the same solution as a maximum likelihood estimator under the assumptions. All the same assumptions we've been talking about all through this course. So ideas behind testing the assumptions of ordinary least squares regression apply just as well to multiple regression. And the math turns out to be the same. So far, everything looks like a simple extension of what we've done so far. But there are some new things in multiple regression, some unique issues that we have to deal with. One of them is called interaction. The predictor variables aren't always independent in their influence on the response. Sometimes we have to deal with interaction. So here's an example where I have two different predictor variables, x1 and x2, but I want to include an interaction term where these two things interact. So here I would include a third term that has x1 times x2 in it. So x1 is pressure, x2 is temperature. Then I would have some interaction term which would be pressure times temperature in the model. Now this makes it, when you have interaction, makes it more interesting. Some would say more difficult. I simply say more interesting in how you interpret the influence of x1 and x2. With interaction, the influence of x1 depends on the magnitude of x2. So we can put that together by thinking of one term as fixed and the other one as a variable. So let's suppose x2 is fixed. It's a constant. Make that constant. Therefore, beta 2 times x2 is a constant. And I can lump it together with the other constant, beta naught. So that becomes, for x2 a constant, that becomes our intercept term. And then I can also pull out beta 3 times x2 as the thing multiplying by x1 and combine it with beta 1. And the slope now becomes beta 1 plus beta 3 times x2. Of course, I can do the same thing assuming x1 is fixed. But in this formulation, for a fixed value of x2, let's say, the resulting equation looks like a straight line. Intercept, slope, only one variable, x1. And often our regressions are based on controlling everything else and then looking only at what x1 does. Now we get to see what this interaction term does. And it can be different. Here's a simple example. Suppose I'm monitoring people's blood pressure, and I notice that people's blood pressure goes up as they get older. And since blood pressure has some correlation with various heart diseases, we want to know when the blood pressure gets too high. So your blood pressure is going up as you age. But blood pressure is also a function of how much exercise you get. So if you have a lot of exercise in your life, then your blood pressure goes down, which of course is a good thing. So we have these two things, age and exercise levels, which influence your blood pressure. How? What is the nature of this influence? Suppose I get a response that looks like this. So I plot blood pressure versus age, low exercise levels, high exercise levels. I get two parallel lines. Well, if I think of x1 as the age, x2 is the exercise level, what I see experimentally is that the slope is constant. If the slope is constant, that must mean the beta 3 term is 0 because x2 is not affecting the slope. If beta 3 is 0, that means there's no interaction. The only thing that's varying is the intercept. Beta 2 is not 0. If I have a finite beta 2, but beta 3 is 0, exercise level is important, but it doesn't cause an interaction term. Sometimes, however, the slope is not constant. As in the second example shown here, I see that exercise does influence blood pressure. The amount of influence is a function of age. So the drop in blood pressure, if I ramp up my exercise level, is more significant when I'm older compared to when I'm younger. The curse of being old. You have to exercise more to keep yourself fit. When you're young, you can pretty much live any life you want and you stay healthy. So what could that mean? Well, one possibility is that the intercept here is independent of the amount of exercise at whatever age I use to start. Maybe it's, as an adult at age 18. The intercept is not a function of the amount of exercise. For in this case, that would mean beta 2 was 0. So the intercept didn't change, but the slope does change. So beta 3 is not 0. And of course, we can have situations where all of these parameters in the model are significant, and beta 0, beta 1, beta 2, and beta 3 are all non-zero. Both the intercept and the slope will vary with both variables. So this is what interaction does. It really does add a lot of complications to the interpretation of the responses. The other thing that's important and new in multiple regression, we're going to spend some lectures coming up in the future on this quite a bit. It's a very, very serious problem in multiple regression called multicollinearity. This happens when the predictor variables themselves are not independent of each other. They're correlated. When one thing changes, the other thing changes. This is called confounding as well as multicollinearity, and we're going to spend quite a bit of time in some later lectures on the topic. Here's an example. I want to know if there are any measures of the body that predict strength. So I have a certain fitness test. I give this fitness test to a bunch of different people, and I want to know, is there some body measure that allows me to predict, to a certain extent, how well they'll do on this fitness test? Well, we find that height is correlated with strength. The taller people tend to do better on this particular fitness test than the shorter people. But I also find that weight is correlated with strength. Way more have a greater strength, or maybe the opposite, but there's a correlation of weight with strength. But height and weight are correlated with each other as well. Tall people way more than short people in general. So I have to ask, are these really two different predictors, or is one good enough? If I have height, then I don't need to have weight. If I have weight, then I don't need to have height. And maybe it doesn't make any sense to have them both in my model if they're both describing the same thing. This would be a problem of collinearity of the two variables, height and weight, and it affects how good our model will be. Let me give you a quick example. This is kind of a fun example. It's a little bit silly, but I hope you appreciate it. Suppose I'm a shampoo manufacturer. I go out and I buy a data set. Somebody's gone and measured all these population characteristics. And I want to build a model to help me predict how much shampoo I'll be able to sell to certain kinds of people. And the data set doesn't have shampoo consumption in that data set, but it's got length of hair. I have some knowledge that people with longer hair use more shampoo than people with shorter hair. Look at my hair. I use very, very little shampoo. One bottle of shampoo and I'm done for the year. Right? So it would make no sense to target me as a consumer of this shampoo manufacturer because my hair is so short. So length of hair is in this data set, and so they want to build a model of what other characteristics impact the length of the hair of the person, and therefore maybe how much shampoo they will consume. Well, they start looking around and looking for correlations, and they find, surprisingly, that hair length is negatively correlated with height. In other words, short people have longer hair than tall people. Well, that was kind of shocking. I mean, I can't say I've ever noticed that before when I look around and I see people, and do I really notice that all the tall people have short hair and all the short people have long hair? Well, the model is significant, and what does it mean? Well, it turns out that I was missing an important predictor variable, gender. Well, women tend to have longer hair than men on average, and women on average are shorter than men. So if I left gender out of the model, I would find a negative correlation of hair length with height. But as soon as I include gender in the model, I find that height completely disappears as a significant predictive variable and should be left out completely. As you might expect, height really doesn't matter when it comes to predicting hair length, but gender does. So you got to find the right predictive variable. And because height and gender are correlated, including them both makes no sense whatsoever. All right, we'll come back to those kind of topics later. Let's talk about this building a model process in very, very general terms, and then we'll get into more specifics as we go along in future lectures. The first question that you have to answer when trying to build a model is trying to understand which predictive variables should be included, right? Have you left out any important predictors that are influencing your output that need to be in your model? But you don't want to include any unnecessary predictors. Have you stuck something in the model that really doesn't influence the output? That's the first question. Which are the right predictor variables to use? The second question is, what is the functional form? And should I have x or x squared or log x or e to the x? I have lots of choices of the functional form for the model itself. Often we have a theory that guides us in this form. Sometimes the theory is very, very rigid. It's well known. We understand it. The only thing that matters is coefficients of the model, but we know exactly what the functional form is. Often that is not the case, though. Even if we have some theory that's guiding us along, there's often several choices still available to us. And we still can choose between including or not including a specific predictor variable and making the functional form one equation form versus another. Often the answers to these two questions depends on the purpose of our model. So let's review again. I think we've talked about this in the past. Let's review again purposes of building a model. There's three general ones, three ones that are most common. One is predictive ability. We want a model to be able to make predictions of what I would be under certain cases of inputs. If we're predicting the model output, that means we want a small standard error of y hat. Y hat is the output of the model. Small value of the uncertainty, the standard error at y hat. We don't really care about the standard errors of the coefficients themselves, the beta k's or the bk's for our specific data set. What we want to avoid is overfitting, but we don't want to fit the noise, but the form of the model is not that important to us. We need to think about model scope, and this is going to be true for all of our kinds of modeling, but we don't want to try to predict y hat or range, which are input variables have not been used to generate that model. What is the range of predictive variables over which our predictions are valid? That's the model scope. Another purpose of a model might be control. I'm measuring the output of something and it's not what I want it to be. I want to change inputs to this process to move the output to where I want it to be. How much? What are the right input variables in order to get the output to move? Here I want small values of the standard errors of the model coefficients. I want to know the slope accurately. So if I want to cause the output to move by 3, how much do I have to move? Input, that depends on getting the slope accurately. And of course, manufacturing, there's lots of examples where control is the purpose of the model. In many cases in science, the goal of building a model is interpretive ability. Of course, this happens in the social sciences and in medicine and lots of other applications as well. We're trying to test or validate a theory, or we're providing an explanation for what's going on. Here's some interesting things in the data, explain it. For this case, we want both small standard errors of the predicted values and small standard errors of the coefficients. And we can't really emphasize one over the other. If interpretive ability is the purpose of our model. So when we start building a model, we often strive for parsimony. That means simplicity. You want the least number of model parameters in the simplest equational form for that model that does a good enough job of describing the data. So you want a model that's consistent with the data on hand. You also want it to be consistent with what you know about the problem, the outside theory or understanding that you bring to the problem. Given that, you want the simplest model you can make. Henri Poincaré had a great discussion of this more than a century ago, and he said, well, of course, whatever model fits the data, you can always make the model more complicated by adding extra terms. You can make it as complicated as you want. But what we want to get is the simplest model that does a good enough job with our data. But sometimes you start with a simple model that's not good enough, so you can add more predictor variables, you can add more complex functions of the predictor variables, you can add more interaction terms. Every time you do that, your model gets better. But you run the risk of starting to fit the noise by adding too many terms. And this is the balance that we try to achieve. How do we know that the added terms are helping or fitting the noise? We have the R-squared term that we've looked at before, the coefficient of determination, correlation coefficient squared. Every time you add a new model term, R-squared always improves. So when I'm comparing two models, I can't use R-squared as a way of saying one model is better than another, because unless they have the exact same number of model terms, the one with more model terms in general have a better R-squared. So we need something more, comparing a model and slowly building a model by adding more variables or functional forms. How do we decide when we're begin to overfit? This will be the subject of the next lecture, and in fact some future lectures after that as well. But this will kind of give you a hint as to where we're going. All right, let's review. What have we learned in this introduction to multiple regression? As always, you should be able to quickly and easily answer these questions. If not, please go back and review the material. Define multiple regression and how it applies to both bivariate and multivariate data. What mathematical techniques are used for OLS, ordinary least squares, multiple regression? Explain interaction and what that means for multiple regression. Explain multicollinearity, what that means for regression. And finally, provide 3 unique purposes for a model. Well, all of these topics are going to be discussed in more detail in coming lectures, but till then.